And that worked.
You got it? Okay.
Okay. Can you guys see that? All right, I'm going to assume that you can see that, so I'm going to proceed. Thank you so much for having me. I'm Bashar Risk. I spoke here last year, and I have the date marked there on the slide, which is March 7th, 2020. Today, it's almost 11 months later, and OSIRIS REx has experienced the successful sample acquisition, and it's stowed the sample, and right now it's some 100 kilometers away from BENNU on its way back, where we hope to do a farewell observation in a couple of months. This wasn't in the original plan. We were just going to get out of Dodge, but there was so much push back from just about everybody that we wanted to look at the asteroid again and see what we had done. So let me just quickly go through what I talked about last time, which is in this pretty extensive list. I tried to include a slide from every aspect of the mission. We had gotten to the point where we had gone by the Earth and gotten a gravity assist from the Earth, and we recorded this image of the Earth-Moon system during that event. Then we, the following year, approached the asteroid over a period of several months, and we took this series of videos, and I hope that the video is coming through, and I'm going to quickly shunt to the Q&A and see if everything's great. Okay, good. It looks like everybody's fine. So that approach, once we got to the asteroid, it went from a point source to an actual body, and we entered what was called proximity operations, which was a highly choreographed series of passes around the asteroid, culminating in us taking an orbit around the asteroid, first at 1.5 kilometers and then at 1 kilometer. Both of those orbits set records for the smallest orbit ever acquired around a planetary or minor body. And then we started taking increasingly detailed images of the surface of the asteroid, culminating in an image at which I show here, which I also showed a year ago, where we were actually able to resolve particles on the surface at our down-selected sample site, smaller than 2 centimeters, which meant that we would be able to have probably a successful sample event, because the throat of our sample head was actually limited to about 2 centimeters. That was the maximum size that the mylar flap could open to receive a sample. So since last March, so now that was all we talked about previous year. Since last March, which March 2020, we've conducted reconnaissance on both our primary site, which you just saw, and our backup site. I'm not going to talk about that. And I'm not going to talk about it, the practice checkpoint and match point maneuvers. And the reason is that it would just take too much time to reprise the events of the last year. I'm going to skip directly to the 8-day period between October 20th and October 27th, when we acquired what we thought was successfully was the sample, and when we closed up the sample head and guillotined the arm at the wrist, which basically is a absolute event. You can't go back from that event, and we only do that with if we have high confidence that the sample was in the sample head. So for those period of 8 days were really the most intensive of a very intensive mission, and so I'm going to focus on them, and hopefully the videos will work, and hopefully you guys will ask questions and get them successfully answered, but here goes. So the first video I'm showing here, and I'm going to show it and then hopefully check and make sure everybody got to see it. This is a succession of some 200 or so images that were taken by our two MAPCAM and SAMCAM are two of our three scientific cameras. They show the spacecraft with its sample arm extended, getting closer and closer to the surface of Bennu on its way to taking a sample. This was, by the way, I've sped up this image by a factor of 37 or so. So what was a half an hour of video is actually 49 seconds. So you'll see here the final sample, and then you see the event, and it's gone. We just saw it. So that was the sample event, and that series of videos, which just looks like a nominal record of what happened during those period of half an hour, is actually going to figure quite strongly in the rest of this presentation, which is just basically you'll see at the end of it what I'm trying to convey here, but in describing the events that happened in the 8-day period, I think we're going to draw some lessons about this kind of mission, and in fact, all kinds of rocket-like missions. Somebody
sorry.
have a yeah,
yep.
Go ahead, Todd.
Bashar, sorry to interrupt you here. It looks like we're having the slides aren't moving forward, and
okay.
It doesn't look like we're in slideshow mode, so the screen is rather small.
Let me stop sharing and then start sharing again. And I was afraid this was going to happen, but let's just see if I can't share the actual slideshow. All right, now this should do that. So, you getting the slideshow now, Todd?
Yep, it's moved. It's
Todd, why don't you stay on, man? I think it's useful if you stay on, and then.
Yep, I'd be happy to.
Yeah, that would be
sure.
Great. Thank you.
Okay.
So this is that video I was just talking about, which you guys didn't see. So I think I explained just about everything about this video, except you didn't get to see it. So why don't you guys just take a gander here first, and then we'll move on. So this is the SAMCAM now. And then this is switches back to the MAPCAM. This here is meant to well, never mind. I'll explain later when we slow it down. That was the bottle release, and then very quickly we backed away. Okay, so let's just pick this apart a little. That half an hour of video consisted of the following sets of events. So am I coming through, Todd?
Yep, I'm hearing you just fine, but it looks like, are you still on the SANDCAM?
No,
photo?
Right now I'm in a table of numbers and figures. Can you see that? Todd, are you there?
Yep. Yes, I'm here.
Okay. Can you see the table I'm showing right now?
No, we're having some kind of difficulty here where, let's try this. Can you refresh your screen one more time?
All right, let's try refreshing here. Okay, that's it. Let's go. Can you see that now?
There we go. Yep, now we've got a set of numbers.
Okay, I'm going to not do anything. In other words, I'm not going to change back to any other screen, but stay on this screen and see. Hopefully that won't screw up the system. But it would be really helpful, Todd, if you would just stay on and give me a little bit of feedback as to how it's going. Okay, great.
Absolutely.
So that whole half an hour is broken out into these like 10 different periods, right? So we have 43 images taken by the MAPCAM as we approach what was called checkpoint. That was our one of our two points of no return, right? So the checkpoint, both of them involve maneuvers and the rockets, the thrusters, and both of them are critical to trying to get precisely to the target that we wanted to get to. When we originally planned this mission, our error in the targeting was supposed to be 25 meters. When we got to Bennu and observed how rocky it was, we knew that wasn't going to cut it. So instead of going with our primary targeting mechanism or primary targeting methodology, we changed to our backup targeting methodology, which relied on a database of recorded images, basically, of the surface of Bennu on the track that we would be following toward the sample site. By doing course corrections according to where we were relative to this database, we would be able to precisely, hopefully is what we thought, target to to very close to the area we wanted. As it happens, we were successful in this. We instead of having an error of 25 meters in the targeting, we had an error of 1 meter. And the cameras that so this is going to be rather disappointing, but the cameras we used for targeting are not these scientific cameras, but a dedicated set of navigation cameras. I'll show you some images from in a second. So this sequence of maneuvers relied on it's not just 2 thrusts, one at checkpoint and one at match point. So before checkpoint, we took a series of MAPCAM images. After checkpoint, we took another series of SAMCAM images. Then we took a series of MAPCAM images. I think you saw them in the video, switched to MAPCAM, and then we switched back to SAMCAM for the final time. And then we blew the bottle. That was right, what we call tag or touch and go. And then we continued to sink into the BENNU's regolith before we fired the back-away thrusters after a few seconds. And then the last several tens of images are the SAMCAM from SAMCAM during the period of back-away. So that's what you see in this video. So now let's look at the last bit of it. And I'm hoping I'm switching to a video right here. Todd, can you see the video? Todd, are you there?
Yes, I'm here, and it's playing.
Okay, great. Thank you. So what we see here is actual clock time. So it emphasizes the fact that Bennu is a very small body with a very gentle gravitational field, and stuff takes a long time. When you orbit the thing, you're orbiting at a rate of 10 centimeters per second or something. So there's the moment of bottle blowing, and then we continue toward the surface for a bit, and then we fire the thrusters, and you can see that they're agitating the surface now and stirring up a bunch of rocks, and now we start backing away. So the whole thing it takes place in a rather short amount of time for Bennu. So Bennu spent all these millions of years as a rock pile held together by the gentlest of gravitational fields and also other effects like electrostatic attraction. And here we are agitating it, blundering into its surface, and in essence creating an explosion simply by releasing gas from a high pressure bottle of nitrogen. And now we're backing away. So this whole period, which nominally was 2 minutes, I'm showing at its regular and cadence. Now all of this, the debris you see there is the lofted cloud of rock and dust. So we're starting it again, so I'm going to push on. And basically it looks like this, and these are approximate dimensions of what you're seeing there. Solar light is coming in at a very sharp angle. The cloud that initially was stirred up by the nitrogen bottle is roughly conical, we think. And we're seeing also evidence that there was a layer of stuff on top of these rocks, which we stirred up, that got kicked out initially. But this is generally what we think is happening. And this is the video sequence or the GIF sequence that actually made it out into the media. We sped it up again by a factor of 37, just like that first video, and just showed the part where we are just about to tag and release the bottle and then fire the thrusters. Now, what we see here So I'm going to focus on a couple of things, and I don't want to spend too much time on it because there's other stuff to talk about, but it's worth pointing out a few things. One is that these are, by the way, a blinking of two images before and after touch, but before we fire the bottle, right? So the surface is relatively undisturbed, but you can see even at the gentle rate that we're touching the surface of this asteroid, we break the rock underneath the TAGSAM head. Now, why is that important? Well, was a big argument throughout the planning of this mission and through most of proximity operations as to whether the surface of Bennu was going to be hard and difficult to sample like concrete, or soft and relatively easy to sample like cake. So when people argue about this, they're not really arguing per se about the scientific curiosity of what the surface is made of, though certainly that's a component of it. What they're really saying is, are we going to be able to successfully sample, and are we going to be done once we do that first sample attempt? Even though we have bottles for second and third sample attempts, fully legitimate, we don't want to have to use them. We want to be done on the first effort. So right away from this video, you can see that it's in all likelihood that we were successful on that first sample attempt. So that's number one. Another thing you notice here is, again, I'm showing two successive images. And these images, by the way, are 1.25 seconds apart. That whole last sequence was done as fast as the SAMCAM could image, and that's approximately what it could image at about 0.8 hertz. So you see the basically the same scene with the same stretch, but the first image, which is that one, and the second image, which is the darker one, are completely different lighting situations. So in the space of that 1 second, you kicked up a whole bunch of dust and it blocked the light of the sun, which is really quite remarkable. Then, so at this point, I'm just going to show you the context in which these images happen. So on the left, and I'm hoping this is coming through because this is fairly complicated. I'm sorry this is such a video-intensive presentation, but really,
it is coming through. It's coming through.
Great. Thank you, Todd. So on the left, we see the SAMCAM image, and it's tilted so that north is up and south is down and east is to the right, west to the left. And on the left is a NAVCAM image, and this is the actual camera that we use, whose images we use. You can see it's quite wide angle and distorted at the edges, just like you'd expect for a very wide angle imager. This is the actual camera we use to guide ourselves to the surface of Bennu and the actual tag site. So their relative footprints are shown in the center, and on the top left, you can see the sequence that I just described in that table. A couple of seminal events in that sequence are marked by the vertical hashed lines that are colored blue. And at the same time, we're watching the scene contract and expand as we move closer, or sorry, we move further away and move closer to the asteroid. You can also see much better in the NAVCAM image on the right. You can see that lofted cloud that was stirred up originally by the gas bottle firing, and then by the thrusters firing a few seconds later. So I'm going to show this one more time, and then we'll move on. But this all was happened. So October 20th was the day we went in. The images downloaded over a period of several days, and then we made all these movies. We assessed the tag success. We're very happy with the results, even though we were a bit taken aback with the violence of the event. But that was more to the good, because we thought, a particularly vigorous stirring of the surface is only good for us because it puts more sample in our bucket, in our sample head. So one more time with the post tag and post gas bottle firing. So on the left, I'm showing it pretty fast. On the right, I'm showing it slower, so that you can kind of get a sense of the chaos of it. It's really, when you look at a NAVCAM image compared to these SAMCAM images, you can see how how tunnel vision the SAMCAM was relative to the event itself. Okay, and this is a NAVCAM image, and these are just two images, again, back and forth. You can see the shadow of the TAGSAM arm crossing the frame, and in fact, the point of contact is below this image and a little bit left of center. So before the gas bottle fires is the first image. After the gas bottle fires is the second image. You can see that monolayer of, or thin layer of dust that I was pointing to before when I showed you guys the cartoon is evidently getting blown off by the gas bottle in an instant before all the other rocks and debris start getting mobilized. So it darkens the frame in a way that allows you to actually measure its optical thickness, and that's something we're doing right now offline. So after this, so that was evidently a successful tag event. And after this event, what we meant to happen, and I'm not even going to try clicking on that YouTube link at the bottom because who knows what will happen. But if you were to click on that YouTube link at the bottom, what you would see is the spacecraft, the OSIRIS REx spacecraft with its arm extended, spinning like a ballet dancer, very slowly, ponderously, so not a very graceful ballet dancer, but as a ballet dancer nonetheless. Or a skater, and what it is trying to do there is measure the moment of inertia, measure its own moment of inertia when the arm is extended. So that was our primary mechanism for measuring the amount of mass that we collected in that sample head. So that was what was supposed to happen. At the few days after we took performed the tag, we did a post-tag maneuver. In other words, what we did was we collapsed the arm. We pointed the bottom of the TAGSAM head, the place where all the sample was reportedly collected, at our SAMCAM, and we took images of the bottom of that head with our SAMCAM. And I'm about to show you the sequence of images that we took. And there they are. So I don't know how fast these are showing up on your screens, but in my screen, we move the TAGSAM head to successive positions, different orientations, by articulating its wrist, and then we snap images, a series of images with increasing exposure time. And you can see the exposure time increasing because you can see the TAGSAM head getting brighter and brighter to the point of saturation successively. But that's not all you see. What you see are evidently a lot of particles leaving the TAGSAM head. In other words, all of the sample, or maybe a part of it, that we so painfully collected over a period of planning that took 10 years and a proximity operations that took 2, is exiting the TAGSAM head. Now we think it's because we've just agitated the interior of the TAGSAM head by moving the wrist from position to position, and therefore it should die down. But of course, we don't know that at all because we don't have a continuous video feed on the TAGSAM head. That would have been too much. So this is 2 days after tag, and what we see is not only were we evidently very successful at collecting a lot of sample, but the sample is exiting the head because the mylar flap probably is stuck in position. And further examination of these images shows exactly that. So with these two images, on the left, I'm showing an image of the bottom of the TAGSAM head 2 years before tag. This was back in 2018, November. And almost 2 years later, during the actual post-tag period, we have the image on the right. Now, what you see is a very clean interior, and you can't see it because it's very difficult to see, but on this, covering this interior of the TAGSAM head, and I hope you guys can see my cursor, is a transparent mylar flap. That flap it opens inward and allows sample to enter, given the very violence of the tag event, because you're releasing, you're imagine this TAGSAM head cupped downward on the surface of BENNU, and then squirt a bunch of high pressure nitrogen into the cavity, into the compartment underneath the head, and that high pressure nitrogen will stir up all kinds of sample, all kinds of regolith. That regolith will have nowhere to go except up through the head, because you've cupped the head upside down onto the surface. So the gas itself will escape through a mesh grid that lines the wall of this head, and entrained within this flow will be the sample that will get lodged within the head. And that seems to be exactly what has happened on the right. So in addition to all these really bright, overexposed images of these particles escaping, you see a very darkened interior that says, oh my goodness, we have so much sample inside this head. And in fact, so I'm showing here a video sequence of 5 images, 2 of which are before and 3 of which are after, that shows the same point. So you can see the before and the after show 2 markedly different things, starting with the fact that the interior of the head in the before images is quite lit up, but in the after images it's quite dark in the interior, because light doesn't get there, because it counts on going through the head, and in fact can't go through the head because there's stuff in the way. And that is what we've observed in these post-tag images. So I have a little detail here, and what you can actually do if you look very closely is see pebbles and rocks stuck and lodged within this sample head. And you can also see, if you look very, very closely, this mylar flap is jammed open, and hence the mystery of why you're getting all these particles escaping from this head, which is supposedly locked tight, is because this flap has been jammed open because it has been crammed with too many rocks and pebbles. So all this was pretty evident within half an hour of looking at these post-tag images. So what happened that weekend, and these things always seem to happen on a weekend, never during the middle of the week. So that weekend we had big meetings at NASA and in the project, and tried to figure out what we're going to do. And the first thing we ended up doing by committee vote, I'm not on the committee, I was just called to give evidence, was that we were going to cancel that primary sample mass measurement. And the reason for that is, if we were going to swing the arm around like a skater or a ballet dancer, then we were going to create centrifugal momentum that would enhance the ability of material to escape from the tag head. And nobody wanted that. In this sequence of 3 images that I've put in a GIF that I go back and forth, you can actually see stuff that's leaving very well. And it ranges all the way from sub 100 micron or sub 10 micron size to a few millimeter size. And it ranges in shape all the way from spherical particles to flakes. You can see the flakes dancing in the center as they escape the head. All of this stuff is leaving. All the stuff that we're seeing we'll never be able to study because it is gone. Bye-bye. And nobody liked the thought of that. We were able to estimate from doing size frequency distribution measurements of these particles that every time we moved the wrist, we lost about 10 grams of sample. And since the minimum sample that we needed to be successful with the mission was 60 grams, that was that was not a good situation. So the basic result of these meetings we had over the weekend was that we needed to stow the head as quickly as possible before we lost any more material. Now, all that said, the situation wasn't as dire as I'm painting it here. Clearly, we had sample to lose. We had so much in there that it was stuffed to the gills and that we could get rid of it. But nobody wants to sign up for understanding the behavior of a zero-G, zero-G behavior of a sample head that we had no ability to test in zero-G before launch, right? At best, we could put it on a vomit comet and test it to quarter G or something like that. And that had its own problems because we could only do that in a chamber the size of a desk, and nobody wasn't sure what kind of wall effects you were doing or anything. So nobody wanted to sign up for the fact that we weren't going to lose the entire sample because if we kept moving the wrist around. So that's why we did and this is a bit of an aside, sorry. I just stuck these in here because it's kind of interesting. you can actually see particles clinging to these surface sample pads. These pads were designed to sample only the stuff on the surface before we agitated it. And so they were designed to answer a bunch of arguments that people have had for years about what radiation does to stuff on the surface of minor bodies. And anyway, in any case, this is a week after the sample event, and stuff was still escaping every time we moved the bottle. By this time, people had decided we were just going to close up shop and get out of Dodge as fast as we could. So that's ended up being what we did. And this is the moment when we stowed the sample head into the sample return capsule, the SRC, and actually tugged on it by pulling back on the arm to make sure it was actually in there. And you can actually see a few particles escaping on the left after we did that tug, or actually after we jammed it in there. So it clearly, this, you know, after the fact, right? I mean, we've already jammed the thing in there and it's done. But this put a lot of people's mind at ease because it showed that particles went away and they escaped only as a result of stuff that we did. You know, every time we moved the thing, particles escaped, but just sitting there, particles didn't tend to escape. They were pretty well lodged in there. So that made people feel better. So that is kind of the story that I wanted to tell. And, you know, being human, it's perfectly human to want to understand lessons that you've learned as a result of this experience. And I just jotted down a few of them so I could tell them to you guys and hopefully generate some discussion. The very first lesson is when you succeed like this, then just pat yourself on the back and enjoy the success because it doesn't happen very often. You need to do that, okay? Okay, so one thing that I thought was really useful about this whole experience, and useful is in the broader sense here, useful to the project, useful to the goal that we had for this mission. It's important to have discussions, not in formal meetings, but also in informal settings, because in formal meetings, people tend to self-censor. But in informal settings, they will allow themselves, after they had a beer or two, to say things that are on their mind that really worry them, but they weren't willing to say in a formal setting. So I thought that was really important. And I thought a lot of the ideas that became useful when we were trying to figure out what to do after, you know, unexpected events happen, came out of the conversations we had in more informal settings. Second, your plans may go awry, but it is important to plan. When the time comes when you have to analyze data, formulate and plan options, and make decisions rapidly, you have had to practice. You better have had practice in the discipline of asking the correct questions and following through. And that, to me, was as important than whatever you planned at the result of it. When you plan 4, 5, 10, 15 years into the future, you're going to be very lucky if your plans have any relevance to what actually happens. But the process of planning is a very important one to have gone through. Okay, third, consensus is always highly sought after at these meetings, okay? Nobody makes the decision. There are people whose job it is to make the decision, but they don't arbitrarily make any kind of decision because it's crazy, right? You want the opinions of everyone in the room, especially if they're a bunch of smart people. You want all of their opinions, and you want them all to agree if you can get them to agree, okay? In this case, that board, there was one minority opinion. That's it, one out of 25 people, which was pretty cool. And, well, I'm not going to go anymore. Respect anonymity here. One of the downsides to consensus, and this is something you also have to watch out for, is groupthink. And by mentioning that term, I'm dating myself because this was a term that was highly popular in the 60s when people were trying to figure out how we got into the messes that we got into in the 60s. And I'm not going to mention them right now, but I think people have a pretty good idea what we're talking about. You have to cultivate minority opinions, okay? If for no other reason, then you can see that they're crazy, right? Somebody will propose a minority opinion in a forum like this, just so they can argue the devil's advocate point of view. And that's enormously valuable, right? Because you want to follow the chain of logic that a minority opinion or a crazy opinion would lead you down. Okay. Okay, number 5, we still don't know, and by know I capitalized it, right? So you know what I mean? No. We don't know what's inside that sample canister. We think we know based on good evidence, okay? Now that's important to keep in mind. We're going to have to wait 3 years to find out whether we were right or not. We think we're right, but it's only based on evidence that we can see. So based on that evidence, and the possibility of losing additional sample, we canceled the primary confirmation test, stowed the sample, and guillotined the risk. This is an absolute move, but it was a consensus one, and we did it for good reason, right? But it's still gutsy, right? We're all risk averse. So given that experience, we're all risk averse. That's how NASA works. It's its primary language. It's its mother tongue, the language of risk. But if you're going to take a risk, you better get something from it. So that's another lesson. So, and then the cake concrete thing I've already talked about. So that's it. I'm going to stop now and take questions. Oh, I guess I should tell you what the future is going to have. So we've extended the date of departure from BENNU by 3 months. So now we're leaving in May of 2021 at a sweet spot in the trajectory fuel analysis. In other words, we're going to save a maximum of fuel by going at that point. And then we get the sample back in 2023. And it comes, and this is a depiction of the moment of the asteroid departure maneuver, just a fanciful realization. I like this picture because it actually shows the actual sky background, which normally when people show stars, they just show random uniform bright spots. And this is the place at the Utah Test and Training Range where we're coming back, which is the landing footprint. And this is what it looks like on the ground there. Okay, I'm going to take questions now, and I'm going to go back to hopefully you guys are still here. All right, so Q&A here. Okay, question from Stanley. Okay, this is an opinion. In my opinion, space scientists should concentrate on colonizing Earth's moon, Luna. Can we actually, Todd, can we talk? Like,
yep, I'm here, but we can't directly talk to the attendees.
Okay, they can't talk, in other words.
Nope. Okay,
fair enough. Well, I agree, but I would have loved to have more of your opinion. Okay, so I'm looking at the questions, and tell me if I'm answering them out of order. What precautions do you use with the sample in case of being a possible biohazard? So we don't think it's a biohazard because it's been in space for millions of years, being exposed to the radiation of space. So anything that's on it has been sterilized, far past what we think is necessary to kill it. And that's kind of the answer. It's not a perfect answer, but it is the criterion. It does factor into the criterion that NASA uses to determine whether something is a biohazard. And please ask a follow-up if you want. Let's see now. Let's go back. Todd, I think you should moderate because I'm not sure I'm getting everybody's questions in the question they order.
Sure.
Do you have access to the Q&A, buddy?
Yep, I'm looking at the Q&A. I would just start at the bottom of that scroll. What kind of gravity field did you have to work through to do these moves?
Oh, it's like 5 micro-G. Is that a good answer? I wish I got a feedback.
Yep, that's a.
All right, let's keep going.
Yeah. And next one
Are the
is
video images of the sampling event that you showed a stereo pair? Unfortunately, no. We were making stereo pairs throughout the mission whenever we had the opportunity, whenever we actually had a valid stereo pair, and I spent a lot of time doing that, but not for the sample event because it was just a single point in time and from a single point of view. Is there potential that the Mylar flap was damaged and the sample has been lost? There's always that potential, but it didn't look like it in all of the post-tag images. Were you expecting that BENNU was a big pile of rocks loosely held together by? Yes, we were expecting that. Or was the makeup and size of the rocks one of the possibilities you came prepared for? We didn't expect it to be so rocky, and the reason for that is this. We did thermal observations of BENNU beforehand from Spitzer Space Telescope, and that allowed us to work out the thermal inertia. And I'm not sure if you're familiar, but the thermal inertia is sensitive to rock size. So the higher the number of the thermal inertia, the bigger the rock is that you expect to find, the bigger the boulder, then I should say. We got a fairly low thermal inertia. And in fact, by analogy to the minor body Itokawa, which Hayabusa 1 visited it back a few years ago, we got a lower thermal inertia than that, and the mean particle size on Itokawa was around 4 centimeters. So we were figuring, that the surface was dominated by the stuff in the few centimeter range, which, of course, because of the dispersion of the particle population, would include stuff that we could sample less than 2 centimeters. When we got there, instead, what we found is huge boulders. I mean, huge. And we didn't observe very many of them from the radar data, not Spitzer, but radar now, which we could have. So everybody was shocked. And it turns out that the thermal inertia measurements are not sensitive to the overall size of the boulders, but the mono units that are smaller and apparently the boulders consist of. That's the best explanation I have. It's still quite a controversial subject. It's turned that field a little bit upside down, and the ramifications are still being worked out. So we were not ready to have BENNU be as bouldery as we found it. All right. Congratulations. Could you please discuss how much of the tag events were pre-programmed to respond to your external commands? Not really at all. Ground in the loop, even though we were only 15 minutes light travel time away when tag happened, was not possible and was not desirable. So we put all the autonomy on the spacecraft to decide. We simplified its job. You know how that Gary Larson cartoon, when you have a bunch of things wrong with the horse, and then the right-word column was always shoot the horse, shoot the horse. In the case of tag, the correct response in practically all the non-nominal cases was abort tag. So we would leave the trajectory that you're on, go back to orbit, and try again. And that was, it's surprising given the number of ways that we could have aborted that we didn't abort ever. Not during a practice, not the first practice, not the second practice, and not during actual tag. Okay, is your plan? I feel like I've flipped the questions. Anyway, I'll just ask this question from Steve. If the plan is to tag another asteroid or surface on a future mission, what would the team do differently? We're not going to be able to tag another asteroid because, unfortunately, we cut our our arm off at the wrist with the guillotine, and we're sending back the hand. So we'll never be able to pick something up. We will be able to jam the arm in to the surface of an asteroid, and that might be something that we would do. Would we do anything differently? I don't think so. We were fairly successful on this mission. I think everybody sees that. We of course, have to examine what comes back in 3 years to make sure of that. But right now, I think people are feeling like we did what we set out to do, which is to arrive at a place we'd never seen before, never been before, didn't know much about, learned all that we could at that spot, learned all that we could about our techniques for approaching and touching that spot, and then carried them out. And in every successive year we were there, we knew more than the year before and operated more successfully. So in that sense, I think we were at kind of our peak of skill by the time we formed tag. How am I doing on time here? Okay, good. I got 10 more minutes. Given the 3-year wait to the retrieval of the sample container, what will the team be focused on doing? Right now, there's a bunch of different efforts. The primary effort is focused on planning the science that we need to get done because of the limited funding cycle. You want to have all your ducks in a row lined up, planning the science that will be done with that sample. So most of that sample is going to be archived, assuming it's anything more than like 50 grams. Even if it is 50 grams, if it more than like 5 grams, because you don't need a lot these days. They have really sensitive analytical instrumentation. You're able to make grand conclusions out of like a nano unit of material. Yeah, so they're planning all that. The second thing we're doing is we're analyzing all of the tag, post-tag, and pre-tag data. And that's a huge effort. Okay, I think that's enough of an answer on that. Precautions, we got that. How deep do we think the layer of loose regolith is on BENNU? That's a great question. It's deeper than we thought it was before tag. I'll tell you that. It's probably around a meter, but that's just my own personal answer based on what I've observed in the last few months. So it's going to need a little bit more analysis, but it's deeper than what we thought it was. Can you go back and show the first? I'm sorry, I lost that. Back and show the first. As you guys add stuff, so it scrolls my screen. So give me a second while I locate what I just saw.
He was asking to see the first 8 slides that got when we got stuck.
Yeah. Hold on a second. Let me see if I can't do that. I probably mess everything up, but it's worth a try. That's not it. You know what? I'm just going to show it too because I'll screw things up if I. Can you guys see that?
Yes.
Okay, so the first 8 slides. If I go into slideshow mode, you won't see it, but I'll tell me what is it that we want to see here, and I'll blow this up a little.
Yeah, I think when we got started, the first, I believe you said 8 slides didn't get shown on the screen of your presentation, and it's okay, Bashar, if we go long.
You sure? Okay.
Yeah, we'll push the next event back so that we can get this in.
You guys are way too kind. Let me just quickly share. I'm going to start my slideshow and then share that, and then we can just have a look-see. Okay, that's good. All right, so I'm just going to step through them now, but assuming I can get into slideshow mode. Here we go.
Okay, we've got right off. Can you refresh your screen?
Yeah.
It's gone. Okay. Oh, there we go. There it is.
Oh, you got it? Okay, good.
No, wait. It's not loading, so I'm going to ask you to refresh your screen.
Yeah, let me refresh my screen. You know what? I don't want to stop the broadcast. I want to stop sharing though, because I think I have a problem with. Okay, and now let's try sharing the slideshow. Okay, you should be seeing that. Are you?
Yep.
Okay, great.
On Saturday, March 7.
Yeah, good. So this is the third slide. Sorry, the fourth slide. This is the GIF of the approach video. So, you know, it was a point source for most of that fall. And then we see it very quickly turn into a planetary-like object that we start mapping. It's weird. It really is strange to see this. I mean, it reminds me a little Star Wars, except if Star Wars was really nerdy. This is to me, one of the more compelling detailed sample site reconnaissance images, because we were able to demonstrate. So this is close to the sample site, but we would never sample here because, you know, everybody would be scared that it would be too much like concrete, right? You would want to sample in a looser area. But the virtue of concrete is it was nice and smooth, so you're able to see these really teeny tiny particles in relief, you know. And so we totally exploited the shadowing to make sure that we, you know, we're seeing something that we thought we were seeing. And then this is a reprise of what we've done since last March. And this is that original GIF that shows the sampling. And this is sped up by a factor of 37 and shows, and I go ahead and pile all the images from both cameras one after the other, willy-nilly. So we're going closer here. We're on the right, it calls out the range to the surface. So I got 100, 96, 95, 92, 90, 85, 82 meters. As it gets closer and skirts that big boulder, which we called Mount Doom, because it was so scary, it was right next to the sample site. And then this is a lot. So the NAVCAM has a 5 times smaller field of view. So you're seeing on the surface. Now we're back to 5 times bigger field of view. And this is the final approach. We crush that rock and bam, ignite the bottle and then blow the thrusters. And then this is just I think this is where we actually all started seeing.
Yeah, this is where we started seeing.
Yeah. Okay, good. We see nothing. Oh wait, no, I'm still in chat mode. Okay, I'm going to start from the top.
Sure.
Sorry. I know it would cost more, but why not get the probe back to Earth ASAP? Because that's a great question. Because people want an extended mission if at all possible. So right now we have a ton of fuel in the tank, and once we drop the sample off at Earth, we would like to go to another asteroid, preferably a topical one, and have a mission there. So that's what we're proposing to NASA to do, and that's why people wanted to save a bunch of fuel if they could. I mean, other than the fact that it's nice to have fuel in the tank in case something bad happens. So those are the reasons. What have we learned about redirecting an asteroid like this one from an Earth impact trajectory? We have learned 1/2 of what you would need to redirect an asteroid. We've learned what the force pushing the asteroid, let me rephrase, the non-gravitational force pushing the asteroid away from its predicted location, we've learned a ton about. It's matched in many respects the theory that we've had about this area, but it's given us a whole sort of appreciation for the nuances of the problem. Now, the second half of the problem is what happens when you take measures to redirect the asteroid. In other words, you send something close to it that can suck it up in a tractor beam, which is what they call the gravitational effect that something small has on something big, believe it or not. Or you send something explosive that will break it up into a bunch of pieces. Or you send a bucket of paint and paint one side a different reflectance so that it will subtly change its orbit, or do any of a number of crazy things that have been suggested. We don't know yet what would happen if we did any of those things to a real live asteroid. And there are missions being proposed right now to try to figure out what those things are. Let's see, what have we learned? The PBS note. Okay, cool. Piggyback on Douglas's question about the materials you might find. I'm going to go to the materials question from Douglas. What types of materials, metals do you expect to find in your samples? Carbonaceous stuff. That's what we care about right now because it's so closely tied to the emergence of life in the solar system, which right now we still think happened on Earth, but a lot of people are saying, well, maybe it happened in space and we were just seeded with the elements of life on Earth. So the thrust in forming this mission and in planning the Hayabusa mission was to go to a carbonaceous target. Something different from what the Japanese went to on their first try with Hayabusa 1. They went to a stony target, which was Itokawa. On the second effort, they went to an asteroid that was very similar to the one we went to. They called it Ryugu. We called ours BENNU. Both were carbonaceous asteroids. Why is sample arm severed after getting the sample? Because the entire arm would not fit inside the sample return capsule, only the head. And that's the way it was designed. Were there any issues or possible issues closing the sample that housed the sample due to? Not at all. It was completely nominal from the point of view of the way it had been planned. I may have missed it, but if you mentioned it before, but how far away is BENNU? Typically, BENNU is about twice the distance of the Earth from the sun away from the Earth. But BENNU has the virtue of coming practically so close to the Earth that it would be within the orbit of the moon half the time. Okay, not that quite that close, but you get the idea. For all intents and purposes, so BENNU is in a 5 to 6 resonance with the Earth's orbit. BENNU goes around the sun 5 times. Every time the Earth goes around the sun 6 times, and they always meet back at the same spot. That makes BENNU about the next best thing to a satellite to the Earth that you can have. Is there a solid core to BENNU, or is it gravel all the way through? Excellent question. We don't really know. Some people say one, some people say the other. Some people have really cool theories on what's going on in the interior of BENNU. Unfortunately, I don't have time to get into them. How deep do we think the layer? Oh, I think I answered that. What precautions do you biohazard question? Second sampling attempt. Did you ever consider a second sampling attempt and immediate storage? Would the risks have been? What would the risks have been? We did consider it back and forth. Basically, people thought it was too risky and an unnecessary risk, which is even worse than being too risky. People are willing to do, like I alluded to in my lessons learned, people are willing to do risky things as long as they're going to get something from it. But if you've already got a sample, people didn't deem the risk was worth it to go back a second time. Okay, let's see. I got that one. Todd, do you see any other questions that I didn't get to? This is probably a good place to stop.
Yeah, I don't see anything else here. Sounds good.
Okay, great. Well,
you
thank you so much for having me. You guys are a great audience, really, seriously. I wish we could have heard your voices, but, you know, just not to be.
Great. Thank you much.
I'm going to stop the broadcast, Todd.
Yep.